There's a boundary in the universe where the rules of reality fundamentally break. Cross it, and you don't just disappear from view. You vanish from the timeline of everything that exists outside. This isn't science fiction. This is the event horizon, and it represents the most extreme prediction of Einstein's equations, a point where our understanding of physics reaches its absolute limit. Imagine standing at the edge of a cliff where the ground beneath your feet isn't just unstable but mathematically guaranteed to collapse. Except this cliff exists in spacetime itself, and once you step over, every possible future you could have leads to the same destination. The singularity at the center isn't just in front of you anymore. It's ahead of you in time, as unavoidable as next Tuesday. The event horizon isn't a wall you can touch or a surface you'd bounce off. It's a mathematical boundary, a demarcation in the fabric of spacetime itself. Think of it as the universe's most perfect trapdoor, one that only swings in a single direction. Matter, light, information, all can pass through going inward. Nothing ever comes back out. What makes this boundary so profound isn't just its one-way nature. It's what happens to the fundamental concepts we take for granted. Time, space, causality, they all behave differently here. For someone watching from a safe distance, you'd never actually see an object cross the event horizon. It would appear to slow down, redden, and freeze at the boundary, trapped there for eternity. But from the perspective of whatever's falling in, the crossing happens in finite time. No fanfare, no sensation of passing through anything special. Just an irreversible transition into a region where escape becomes physically impossible. The mathematics behind this are elegant but unforgiving. Carl Schwarzschild discovered the solution to Einstein's field equations in 1916, just months after Einstein published his general theory of relativity. Working in the trenches during World War I, Schwarzschild found something Einstein himself hadn't fully anticipated. His equations predicted that for any mass compressed below a certain critical radius, spacetime would curve so severely that it would create this point of no return. That critical radius bears his name now: the Schwarzschild radius. The formula is deceptively simple: 2 times the gravitational constant, multiplied by the mass, divided by the speed of light squared. Plug in the mass of our Sun, and you get about 3 kilometers. Compress the Sun down to a sphere 6 kilometers across, and you'd create an event horizon. Earth's Schwarzschild radius: 9 millimeters. Crush our entire planet to the size of a grape, and spacetime would seal it off from the rest of the universe forever. But here's what most people miss about event horizons. The size of the boundary isn't determined by density alone. It's purely about mass. A supermassive black hole at the center of a galaxy, containing billions of solar masses, has an event horizon measuring billions of kilometers across. Yet near that horizon, the curvature of spacetime per unit volume is actually less extreme than around a stellar mass black hole. This counterintuitive fact leads to one of the strangest predictions in all of physics, but we'll get to that shortly. First, you need to understand what Wolfgang Rindler meant when he coined the term event horizon in the 1950s. An event is anything that happens at a specific point in spacetime. A star exploding, a particle decaying. You reading this sentence. An event horizon is a boundary beyond which events can never send signals to a particular observer. If something happens inside a black hole's event horizon, no information about that event can ever reach someone outside. The event might as well not have happened, at least from the external universe's perspective. This creates a profound asymmetry in causality. Events outside the horizon can influence what happens inside. Light from distant stars, gravitational waves from the cosmos, all of it can fall through. But causality becomes a one-way street at the boundary. The event horizon is what physicists call a null surface, meaning it's defined by the paths that light rays would take. These paths are perpendicular to the horizon, pointing inward, and nothing in the universe can outrun light. David Finkelstein understood this in 1958 when he described the event horizon as a perfect unidirectional membrane. Causal influences can cross it in only one direction. This isn't because of some physical barrier preventing escape. It's because inside the horizon, all future directed paths through spacetime, every possible trajectory you could take, lead deeper inward. Trying to escape would be like trying to travel backward in time. Not difficult. Impossible. The history of understanding event horizons is littered with confusion and resistance. When Robert Oppenheimer and his student Hartland Snyder worked out what happens to a collapsing star in 1939, they discovered something disturbing. As a massive star exhausts its nuclear fuel and gravity overwhelms all other forces, the star's matter falls inward. But from the perspective of a distant observer, the collapse appears to slow down as the surface approaches the Schwarzschild radius. Time dilation becomes so extreme that the star seems to freeze, its light redshifting toward infinity, fading from view but never quite reaching the critical boundary. For decades, physicists debated whether this meant black holes couldn't actually form. Maybe the collapse would take infinite time from any external reference frame, making black holes more of a mathematical curiosity than a physical reality. This confusion stemmed from using the wrong coordinate system, a mathematical framework that broke down at the event horizon even though the physics remained perfectly well defined. The breakthrough came from understanding that different observers experience reality differently near extreme gravitational fields. An astronaut falling toward a black hole and a colleague watching from a spaceship far away would give completely contradictory accounts of what happens. Both would be correct within their own reference frames. The falling astronaut crosses the event horizon in a measurable, finite amount of their own time. The distant observer never sees this crossing occur, watching instead as the astronaut appears to freeze at the boundary, their image fading as the light redshifts out of the visible spectrum. This isn't an illusion or a trick of perception. It's a fundamental feature of how spacetime works near these extreme objects. Time itself flows differently depending on where you are in the gravitational field. Near the event horizon of a black hole, gravitational time dilation becomes so severe that a clock would appear nearly stopped to someone far away. At the exact boundary, time dilation becomes infinite from an external perspective. The clock would never be seen to tick again. But from the clock's own perspective, from the reference frame of anything falling through the horizon, time continues flowing normally. You'd sail past the event horizon without any local indication that you'd crossed a cosmic point of no return. No sign, no sensation, no warning. The transition would be as smooth as crossing the equator while flying in an airplane. You'd only know you'd passed it by looking back and realizing you could never return. What you would notice, eventually, is something far more visceral. Tidal forces. These aren't the gentle tides that pull on Earth's oceans. Near a black hole, tidal forces arise from the difference in gravitational pull between your head and your feet, assuming you're falling feet first. On Earth's surface, this difference is negligible, about 700 thousandths of a percent. Near a solar mass black hole, just 100 kilometers above the event horizon, that difference becomes 6 million times stronger than Earth's entire gravitational field. This is where the term spaghettification comes from, coined by Stephen Hawking. The gravitational gradient would stretch you lengthwise while compressing you from the sides. For a small black hole, this happens long before you reach the event horizon. Your body would be pulled apart into a stream of atoms, then subatomic particles, long before you crossed the boundary. Death would be certain and unpleasant, but at least it would be quick. Here's the strange part, though. For a supermassive black hole, the kind lurking at the center of most galaxies, you could cross the event horizon completely intact. The black hole at the center of our Milky Way has a mass of about 4.3 million times our Sun. Its Schwarzschild radius stretches for roughly 12 million kilometers. At that scale, the tidal forces at the event horizon are barely noticeable, less than 0.02% difference between your head and feet. You could fall through the point of no return without feeling anything unusual at all. This reveals something profound about event horizons. They're not uniform in their effects. The experience of approaching one depends entirely on the mass of the black hole in question. Small black holes are violent, tearing apart anything that comes close. Supermassive ones are deceptively gentle at their boundaries, saving their violence for the approach to the singularity deep inside, where tidal forces eventually become infinite regardless of the black hole's size. The Event Horizon Telescope changed everything when it released the first direct image of a black hole in April 2019. The target was M87 star, the supermassive black hole at the center of the Messier 87 galaxy, located about 55 million light-years away. The telescope isn't a single instrument but a network of 8 radio observatories spread across the planet, synchronized to function as one Earth-sized virtual telescope. The resolution achieved was extraordinary, equivalent to reading a newspaper in New York from a cafe in Paris. What the image showed wasn't the event horizon itself. You can't photograph something that emits no light. Instead, the image captured the shadow of the event horizon, a dark region surrounded by a bright ring of superheated gas spiraling toward its doom. That bright ring is matter accelerating to nearly the speed of light, friction heating it to billions of degrees, causing it to emit radiation across the spectrum before it crosses the point of no return and disappears forever. The measurements were precise. M87 star has a mass of about 6.5 billion times our Sun. Its event horizon measures approximately 40 billion kilometers across. But the shadow it casts is larger, about 5.5 times the size of the horizon itself. This happens because the black hole's gravity is so intense that it bends light from behind it around to the front, creating a gravitational lens that magnifies the apparent size of the dark region. Recent observations in 2026 pushed the resolution even higher, achieving observations at 345 GHz, a 50% increase in detail over previous images. These new observations revealed something unexpected. The polarization patterns of light near M87 star change significantly over time, even though the size of the shadow remains constant. Between 2017 and 2021, the polarization pattern actually flipped direction, something nobody predicted. What does this tell us? The environment near the event horizon is far more dynamic than models suggested. The magnetic fields threading through the accretion disk, the orientation of the infalling matter, these factors create complex patterns that evolve on timescales of years. The event horizon itself remains unchanged, confirming Einstein's predictions. But the region just outside it seethes with activity, matter, and energy in their final moments before crossing the boundary and vanishing from our universe. And that brings us to the most unsettling question about event horizons. What actually happens to information that crosses this boundary? Does it simply cease to exist from the universe's perspective? Can information truly be destroyed? This question has consumed theoretical physicists for decades, creating what's known as the black hole information paradox. The answer might require rewriting our understanding of quantum mechanics, general relativity, or both. But to understand why information matters so much, you first need to grasp what happens to spacetime itself as you approach and cross an event horizon. The geometry becomes so warped that the concepts of space and time fundamentally exchange roles. Inside the horizon, the singularity isn't a place you can avoid going to. It's a moment in your future that you can't avoid reaching. The geometry of spacetime near an event horizon doesn't just bend. It breaks every rule you learned about how the universe works. Think about your everyday experience of space and time. Space is where things are. Time is what happens to them. You can move through space in any direction, forward, backward, left, right, up, down. But time only flows one way. You can't decide to move backward through Tuesday. At the event horizon, those roles swap. Inside the boundary, the direction toward the singularity becomes timelike. Moving toward the center isn't something you choose anymore. It's as inevitable as moving from this moment to the next moment. The singularity isn't somewhere you can avoid going. It's a point in your future that you will reach, no matter what you do. You could fire your rockets at maximum thrust away from the center. Doesn't matter. You're still moving toward it, the same way firing rockets doesn't stop you from moving into next Tuesday. This happens because of how gravity warps the structure of spacetime itself. Einstein's general relativity describes gravity not as a force pulling on objects, but as the curvature of spacetime caused by mass and energy. Massive objects create wells in the fabric of spacetime, and other objects follow the curved paths through that warped geometry. Near an event horizon, the curvature becomes so extreme that all paths, every possible trajectory through spacetime, point inward. Outside the horizon, you still have choices. You can orbit. You can escape if you have enough velocity. You can hover if you fire your engines hard enough. But the moment you cross that boundary, all those options vanish. The mathematics is brutal and absolute. Every light cone, the set of all possible future positions you could reach, tilts inward. There's no trajectory that leads back out. The event horizon marks the point where spacetime curvature becomes so severe that even light, traveling at the maximum possible speed through the universe, cannot escape. But here's what makes this truly strange. From your perspective falling in, you wouldn't notice anything special happening at the event horizon itself. There's no wall, no barrier, no sudden change. You'd cross it without feeling a thing, at least if you're falling into a supermassive black hole. The local geometry at the horizon is smooth. You wouldn't see a sign saying you've passed the point of no return. You just keep falling, and only later would you realize, from the way spacetime behaves around you, that escape is no longer possible. The size of the event horizon depends entirely on the black hole's mass. The formula, derived by Carl Schwarzschild in 1916, gives the radius as 2 times the gravitational constant times the mass, divided by the speed of light squared. For our Sun, that radius is about 3 kilometers. Compress the Sun down to a sphere 6 kilometers wide, and you'd have a black hole. For Earth, the Schwarzschild radius is roughly 9 millimeters. Compress our entire planet to the size of a marble, and it becomes a black hole. What determines whether something is a black hole isn't the mass. It's whether all that mass is compressed within its Schwarzschild radius. Stellar mass black holes form when massive stars collapse at the end of their lives. The star runs out of fuel, its core can no longer support itself against gravity, and it implodes. If the remaining core has enough mass, nothing can stop the collapse. The matter gets compressed beyond the point where even neutron degeneracy pressure can resist, and it forms a black hole with an event horizon roughly 10 to 100 kilometers across. Supermassive black holes are different beasts entirely. They sit at the centers of galaxies with masses millions or billions of times that of the Sun. M87 star, the black hole we imaged in 2019, has a mass of 6.5 billion solar masses. Its event horizon stretches 40 billion kilometers across. That's larger than the orbit of Neptune. And yet, paradoxically, crossing that event horizon would feel gentler than crossing the horizon of a stellar mass black hole. Why? Tidal forces. Gravity weakens with distance, so your feet experience stronger gravity than your head when you're standing on Earth. The difference is tiny, about 0.00007%. But near a black hole, that difference becomes extreme. For a stellar mass black hole with the mass of our Sun, if you were 100 kilometers from the event horizon, the gravity difference between your head and feet would be 6 million times stronger than Earth's gravity. You'd be ripped apart long before reaching the horizon itself. But for M87 star, with its enormous mass and correspondingly huge event horizon, the tidal forces at the horizon are surprisingly gentle. The curvature of spacetime is spread over such a vast distance that the gravity gradient is almost negligible. Calculations show the difference in gravitational force between your head and feet at the horizon of a supermassive black hole would be only about 0.02%. Barely noticeable. You could cross the event horizon of a supermassive black hole without feeling anything unusual at all. That doesn't mean you're safe. Once inside, you're still doomed. The tidal forces increase rapidly as you fall toward the center. Eventually, they become strong enough to tear apart anything, from spacecraft to atoms. This process has a technical name, spaghettification, which is exactly what it sounds like. Objects get stretched into long, thin strands. But for supermassive black holes, that happens well after you've crossed the event horizon. The shape of the event horizon also depends on whether the black hole is rotating. A non-rotating black hole, described by the Schwarzschild solution, has a perfectly spherical event horizon. But most black holes in nature are rotating. They form from collapsing stars or merging compact objects, and those systems carry angular momentum. When a rotating mass collapses, conservation of angular momentum causes it to spin faster, just like a figure skater pulling in their arms. Rotating black holes, described by the Kerr metric derived in 1963, have oblate event horizons, flattened at the poles and bulging at the equator. But rotation does something even stranger. It drags spacetime itself around the black hole, a phenomenon called frame dragging or the Lenz-Thirring effect. Close to a rotating black hole, spacetime is pulled in the direction of rotation. If you tried to remain stationary relative to a distant observer, you'd have to move faster than light relative to the local spacetime, which is impossible. This creates a region called the ergosphere, outside the event horizon, where you cannot avoid being dragged around the black hole. You can still escape from the ergosphere, unlike from inside the event horizon. But you can't stay still. You must rotate with the black hole, even if you're firing your engines trying to resist. The ergosphere is where some of the most exotic phenomena in black hole physics occur, including the Penrose process, a mechanism for extracting rotational energy from the black hole itself. Roger Penrose showed in 1969 that if you drop an object into the ergosphere and split it at just the right moment, one piece can fall into the black hole while the other escapes with more energy than the original object had. The energy comes from the black hole's rotation, slowing it down slightly. Theoretically, you could extract up to 29% of a black hole's mass energy this way. Some physicists think this mechanism might power the enormous jets we see shooting from the centers of active galaxies. Then there's the photon sphere, an unstable orbital region where light itself can orbit the black hole. For a non-rotating black hole, this sphere sits at 1.5 times the Schwarzschild radius. Photons traveling tangentially at exactly this distance will loop around the black hole in circular orbits. But these orbits are unstable. The slightest perturbation sends the photon either spiraling into the event horizon or escaping to infinity. No stable orbits exist at or inside the photon sphere. This is why the shadow we see in images of black holes is larger than the event horizon itself. Light emitted just outside the photon sphere gets bent around the black hole, some of it looping multiple times before escaping. This gravitational lensing magnifies the apparent size of the dark region. The shadow represents not just the event horizon, but the entire zone where light gets trapped or severely bent. What we're really seeing in those images is the last gasp of matter before it disappears forever. The bright ring surrounding the shadow is the accretion disk, superheated gas spiraling inward at relativistic speeds. Friction and magnetic fields heat this material to billions of degrees, causing it to radiate across the electromagnetic spectrum. That radiation is what we detect. But the matter producing it is already doomed, already past the point where any physical process can save it from crossing the horizon. And once it crosses, something even stranger happens. Information itself appears to vanish from the universe. This brings us to one of the deepest unsolved problems in theoretical physics: the black hole information paradox. In the 1970s, Stephen Hawking discovered something completely unexpected. Black holes aren't entirely black. They radiate. This wasn't some minor correction to the theory. It was a fundamental challenge to everything physicists thought they understood about how the universe works. Here's the setup. Quantum mechanics tells us that information cannot be destroyed. Ever. If you burn a book, the information isn't lost. In principle, if you could track every atom, every photon released in the flames, you could reconstruct what was written. The laws of quantum mechanics are reversible. Given the final state of a system and the laws of physics, you can work backward to determine the initial state. This principle is absolute. Non-negotiable. General relativity, however, says something different. When matter falls into a black hole, it crosses the event horizon and disappears from a universe. The black hole's mass increases, but all other details about what fell in are erased. A black hole is characterized by exactly three properties: mass, electric charge, and angular momentum. That's it. Whether you throw in a pile of encyclopedias or an equivalent mass of hydrogen gas, the black hole looks identical afterward. This is summarized in the phrase, black holes have no hair, meaning they have no distinguishing features beyond those three numbers. So far, maybe that's fine. The information crossed the horizon. It's still there, just inaccessible. Locked inside forever. But then Hawking showed that black holes evaporate. Hawking radiation arises from quantum effects near the event horizon. In quantum field theory, empty space isn't truly empty. Virtual particle-antiparticle pairs constantly pop into existence and annihilate almost immediately. Near a black hole's event horizon, these pairs can be split. One particle falls into the black hole. The other escapes as real radiation. From a distance, it looks like the black hole is emitting thermal radiation. The temperature of this radiation is inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is about 1/10,000,000th of a degree above absolute zero. Incredibly cold. Far colder than the cosmic microwave background. So stellar mass black holes actually absorb more radiation than they emit. They grow rather than shrink. But if a black hole is isolated, if it stops accreting matter, it will eventually radiate away all its mass. A solar mass black hole would take 10 to the 67th years to evaporate. far longer than the current age of the universe. But a microscopic black hole would evaporate in a fraction of a second. Here's where the paradox emerges. As the black hole evaporates, it shrinks. Eventually, it disappears completely. When it's gone, what happened to the information that fell in? Hawking's original calculation suggested the radiation is completely thermal. Random. It carries no information about what fell into the black hole. The information would be destroyed. Quantum mechanics violate it. This sparked decades of debate. Some physicists argued the information must somehow be encoded in the radiation, even if we don't yet understand how. Others suggested information might be preserved in subtle correlations between the particles. A few proposed that general relativity itself breaks down before the information is truly lost, perhaps through some quantum gravity effect we haven't discovered yet. There's even a proposal that information could tunnel out through quantum effects we don't fully understand, leaking out gradually during the evaporation process. Recent work suggests the information might be encoded in the radiation after all, but in a way that requires considering quantum entanglement across the event horizon. When you account for entanglement properly, the radiation might not be purely thermal. It might carry encoded information in correlations that only become apparent when you analyze the entire history of the evaporation. This doesn't solve the paradox completely. It shifts the question. How does information get from inside the horizon to the outgoing radiation without anything crossing back out? One proposed solution involves something called the firewall paradox. If information must escape, and if quantum mechanics is correct, then the event horizon might not be the smooth, uneventful place we thought. There might be a wall of high-energy particles right at the horizon, a firewall that would incinerate anything trying to cross. This preserves information but violates the equivalence principle, the idea that freely falling observers shouldn't notice anything special at the horizon. Another approach involves holography. The holographic principle suggests that all the information about a three-dimensional volume can be encoded on its two-dimensional boundary. Applied to black holes, this means all the information about what's inside could be encoded on the event horizon itself. The horizon becomes like a hologram, storing information about the interior in its structure. When the black hole evaporates, the information is released through the radiation. This is mathematically elegant but conceptually bizarre. It suggests that the three-dimensional interior might be, in some sense, an illusion. A projection of information stored on the surface. We still don't have a definitive answer. The information paradox remains unresolved. It's a sign that our understanding of either quantum mechanics or general relativity, or both, is incomplete. Most physicists suspect the resolution will come from a theory of quantum gravity, a framework that unifies quantum mechanics with general relativity. String theory and loop quantum gravity are the leading candidates, but neither has yet provided a clear, testable solution to the information paradox. What makes this so profound is that it's not just an academic puzzle. It strikes at the foundations of how reality works. If information can be destroyed, the universe is fundamentally random at a level we never imagined. The past wouldn't determine the future. Predictability would break down in a fundamental way. Everything we think we know about causality, about the arrow of time, would need revision. But there's another layer to this. Hawking radiation has never been observed. We've never seen a black hole evaporate. The temperatures are too low, the timescales too long. Everything about this paradox rests on theoretical calculations, brilliant and rigorous, but untested. We're debating the fate of information based on equations, not experiments. That might change. Some physicists have proposed creating analog black holes in laboratory settings. Not real black holes, but systems that mimic their behavior. Sound waves in flowing fluids, for instance, can create acoustic horizons that behave mathematically like event horizons. If Hawking radiation exists, there should be an analogous effect in these systems. Early experiments have shown hints of this, though the results remain controversial. And there's one more twist to consider. If black holes evaporate completely, they might not disappear entirely. Some theories predict a remnant, a tiny stable object left behind when the evaporation process ends. This remnant would contain all the information that fell in, compressed into a nearly Planck-scale object. The Planck scale is the smallest meaningful length in physics, about 10 to the minus 35 meters. A remnant would be unimaginably small but incredibly dense, potentially containing unlimited information. This solves the paradox but raises new questions. How can something so small store so much? What would such an object even be? The information paradox isn't just about black holes. It's about the limits of knowledge itself. What can we know about regions of spacetime cut off from observation? If information truly vanishes, can we ever claim to understand the universe completely? These questions push physics into philosophical territory, forcing us to confront what it means to explain reality. And here's what keeps physicists awake at night. The paradox might not have a resolution within the framework we're using. It might require abandoning assumptions we consider fundamental. Time, space, causality, information itself. The event horizon is where these concepts meet their limit, where the rules we trust start to fracture. So maybe the answer lies in rethinking what an event horizon actually is. Because not all event horizons are created equal. We've been treating black holes as if they're all variations on the same theme. A mass collapses, space-time curves, an event horizon forms. But reality is messier. Black holes come in different flavors, and their event horizons behave differently depending on a single critical factor. Rotation. A non-rotating black hole is described by the Schwarzschild metric, named after Karl Schwarzschild, who derived the solution in 1916 while serving in the German army during World War I. It's a perfectly spherical event horizon, symmetric in every direction. Simple. Clean. Probably doesn't exist anywhere in the universe. Because everything rotates. Stars rotate. Galaxies rotate. When a star collapses into a black hole, it carries that rotation with it. Angular momentum is conserved. The result is a rotating black hole, described by the Kerr metric, discovered by Roy Kerr in 1963. And rotating black holes are strange in ways that make non-rotating ones look tame by comparison. The event horizon of a Kerr black hole is oblate, flattened at the poles, bulging at the equator. But that's just the beginning. Around this horizon lies another boundary, something that doesn't exist for non-rotating black holes. The ergosphere. The ergosphere is a region where spacetime itself is dragged around the black hole. Not pulled in, but twisted. Imagine standing on a rotating platform. If you stand still relative to the ground, you're moving relative to the platform. Inside the ergosphere, if you try to remain stationary relative to distant stars, you'd need to move faster than light. Which you can't. So everything inside the ergosphere is forced to rotate with the black hole, whether it wants to or not. This is called frame dragging, or the lens-stirring effect. Spacetime is not a passive stage. It's dynamic, responsive. A rotating mass grabs it and twists it like fabric. The faster the rotation, the more extreme the twist. Near a maximally rotating black hole, the ergosphere extends outward significantly from the event horizon. It's a region where the normal rules about motion start breaking down, but you're not yet doomed. Because here's the crucial difference. You can escape from the ergosphere. It's outside the event horizon. If you have enough thrust, enough energy, you can fight your way back out. The event horizon is still the point of no return, but the ergosphere is a warning zone. A place where physics gets weird but not yet fatal. And there's something even stranger. You can extract energy from a rotating black hole. This was Roger Penrose's insight in 1969. The Penrose process. Send an object into the ergosphere, have it split into two pieces, one falling into the black hole, the other escaping. Under the right conditions, the escaping piece can carry more energy than the original object had. You've stolen rotational energy from the black hole itself. The maximum energy you can extract from a single particle is about 20% of its mass energy. Keep doing this, and you could theoretically harvest up to 29% of the black hole's total mass energy. That's vastly more efficient than nuclear fusion, which converts less than 1% of mass into energy. A rotating black hole is the universe's most powerful battery. At least in principle. This might explain some of the most energetic phenomena we observe. Quasars. Gamma-ray bursts. Jets of matter streaming away from black holes at nearly the speed of light, extending for thousands of light years. These jets carry staggering amounts of energy, and they seem to originate from the ergosphere region. The Penrose process, or something like it, might be powering them. But there's a limit. As you extract energy, the black hole slows down. The ergosphere shrinks. Eventually, you drain all the rotation, leaving a non-rotating Schwarzschild black hole. A cosmic engine running out of fuel, though on timescales far longer than the current age of the universe. Now consider what this means for the event horizon itself. In a rotating black hole, the event horizon isn't where you might think. It's not at the Schwarzschild radius. It's smaller, pulled inward by the rotation. For a maximally rotating black hole, the event horizon can shrink to half the Schwarzschild radius. The rotation is fighting against collapse, in a sense, creating a more compact but also more complex structure. And inside the event horizon of a rotating black hole, things get even stranger. There's another boundary. The inner horizon. In the mathematics of the Kerr solution, you don't immediately hit the singularity after crossing the outer event horizon. You enter a region where the properties of spacetime flip. Time and space exchange roles again, but differently than before. Then you cross the inner horizon. What lies beyond the inner horizon is where the math goes completely off the rails. The singularity of a Kerr black hole isn't a point. It's a ring. A circular singularity with finite radius, rotating at incredible speed. And according to the equations, if you could somehow pass through the center of this ring without hitting it, you'd emerge into a region with bizarre properties. Negative masses. Closed time-like curves. Pathways that loop back on themselves in time. This is almost certainly unphysical. Most physicists think the inner horizon is unstable, that quantum effects or small perturbations would destroy it. It's likely an artifact of the mathematical idealization, assuming a perfectly rotating black hole in perfect isolation. Real black holes aren't perfect. They're messy, fed by infalling matter, buffeted by external forces. The inner structure probably doesn't match the clean Kerr solution. But we don't know for sure, because we can't look inside. The event horizon blocks all information. The inner workings of a black hole are speculation, guided by mathematics but untested by observation. Here's what we can observe, though. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole. M87 star. A supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. The image showed exactly what theory predicted. A bright ring of light surrounding a dark central shadow. That shadow is not the event horizon itself. It's larger. About 2.5 times the diameter of the event horizon. The shadow is the region where light rays are bent so severely by the black hole's gravity that they either fall in or complete multiple orbits before escaping. The boundary of the shadow is determined by the photon sphere, where light can orbit the black hole. The photon sphere sits at 1.5 Schwarzschild radii for a non-rotating black hole. It's an unstable orbit. Photons circling at this exact distance will continue circling, in theory, forever. But the orbit is unstable. The slightest perturbation sends them either spiraling inward or escaping outward. It's a razor's edge in spacetime. This photon sphere is why we can see the shadow at all. Light from behind the black hole gets bent around it, creating a ring of light that outlines the darkness within. The ring is an accretion disk, superheated matter spiraling inward, glowing at millions of degrees. The shadow is the absence. The place where light cannot escape, even indirectly. The Event Horizon Telescope measured M87 star's mass at 6.5 billion times the mass of the Sun. The event horizon diameter is about 40 billion kilometers. That's roughly the size of our entire solar system. And yet, from 55 million light-years away, we resolved it. We saw the shadow of an event horizon. In 2026, the EHT achieved even higher resolution, observing at 345 GHz. 50% more detail. Enough to see changes over time. The ring of light isn't static. The polarization patterns shift. Between 2017 and 2021, they flipped direction. Nobody expected that. It suggests the magnetic fields around the black hole are dynamic, reorganizing on timescales of years. This is critical because it means we're watching the environment just outside the event horizon evolve in real time. We're seeing the last moments of matter before it crosses the point of no return. The data is telling us something about how black holes feed, how they launch jets, how they interact with their surroundings. And there's more. The EHT has now imaged Sagittarius A star, the supermassive black hole at the center of our own Milky Way. It's much smaller than M87 star, only about 4 million solar masses. Its event horizon is about 24 million kilometers across, roughly 17 times the diameter of the Sun. But it's also much closer, only 26,000 light-years away. Sagittarius A star is harder to image because the material around it changes on timescales of minutes. M87 star is relatively steady, fed by a continuous stream. Sagittarius A star is more erratic, flickering and flaring. Capturing a clear image required sophisticated algorithms to piece together observations taken over hours, compensating for the turbulence. But we got it. Another ring of light. Another shadow. Confirmation that our understanding of event horizons, at least at this scale, matches reality. The shadows are the right size. The brightness distribution fits. General relativity holds. Yet these observations also raise questions. The jets from M87 star originate very close to the event horizon, possibly within the ergosphere. How exactly does that work? How does rotation and magnetic fields and infalling matter combine to launch coherent streams of particles across intergalactic distances? We have models, but the details are murky. What we're seeing is the silhouette of something we can never touch, never probe directly. The event horizon remains hidden. What we observe is its effect on everything around it. The bending of light, the heating of gas, the twisting of spacetime. We're mapping the invisible through its influence. And this is where things get genuinely strange. The event horizon isn't just hiding something we can't see. It's hiding something that challenges the very foundation of how we understand information and reality itself. Stephen Hawking proved in the 1970s that black holes aren't completely black. They emit radiation. Not from inside the event horizon, but from just outside it. Quantum effects near the horizon create pairs of particles. One falls in. The other escapes. This is Hawking radiation. And it means black holes slowly evaporate. They lose mass over time. For a black hole with the mass of our Sun, this process takes 10 to the 67th years. That's vastly longer than the current age of the universe. For supermassive black holes, it's even slower. 100 billion solar mass black hole would take 2 times 10 to the 100th years to evaporate. These aren't timescales we can observe. But the physics is real. And it creates a problem. When Hawking first calculated this radiation, he found something disturbing. The radiation appeared to be completely random. It carried no information about what fell into the black hole. If you threw a book into a black hole, the information in that book, every letter, every word, would be destroyed forever. This violates a fundamental principle of quantum mechanics. Information cannot be destroyed. In quantum theory, if you know the complete state of a system at one moment, you can, in principle, reconstruct its past or predict its future. Information is conserved. But if black holes destroy information, then quantum mechanics breaks down. This is the black hole information paradox. And for decades, nobody knew how to solve it. Some physicists argued that information does escape, encoded somehow in the Hawking radiation. Others suggested that information is stored at the event horizon itself, imprinted on the surface in a way we don't yet understand. This idea led to the holographic principle. The notion that all the information inside a volume of space can be encoded on its boundary. Like a hologram, where a three-dimensional image is stored on a two-dimensional surface. The event horizon might work the same way. Every particle, every photon that crosses the horizon leaves an imprint. The information isn't lost. It's scrambled. Encoded in patterns we can't yet decode. Recent theoretical work suggests this might be correct. Quantum entanglement, the phenomenon where particles remain connected across distances, might survive even after one particle crosses the event horizon. There's a tiny, statistical signature that remains detectable outside. It doesn't let information escape in a useful way. But it suggests the boundary between inside and outside isn't as absolute as we thought. The paradox remains unsolved. But it's telling us something profound. The event horizon is more than a geometric boundary. It's a place where quantum mechanics and general relativity collide. Where our two most successful theories of physics give contradictory answers. And until we reconcile them, the event horizon will remain mysterious. Not just observationally, but conceptually. Now consider what happens if you actually fall toward one. Not in theory. In practice. If you fell toward a stellar mass black hole, say 10 times the sun's mass, you die long before reaching the event horizon. The tidal forces would rip you apart. Your feet, closer to the black hole, would experience vastly stronger gravity than your head. The difference in gravitational pull across your body would stretch you into a thin stream of atoms. This is called spaghettification. For a black hole with the sun's mass, the tidal forces at the event horizon are catastrophic. The difference in gravity between your head and feet would be 6 million times Earth's surface gravity. No structure, biological or mechanical, could survive. You'd be torn apart roughly 100 kilometers above the horizon. But here's the twist. For a supermassive black hole, the tidal forces at the event horizon are weak. Sagittarius A star, with 4 million solar masses, has an event horizon about 12 million kilometers across. At that size, the curvature of spacetime is gentler. The tidal force across a human body at the horizon is only about 0.02% of Earth's gravity. Barely noticeable. You could cross the event horizon of a supermassive black hole and feel nothing. No pain. No sudden change. You'd pass the point of no return without even realizing it. From your perspective, time continues normally. You don't see the universe freeze. You don't experience time dilation. You just keep falling. The event horizon, for you, is not a dramatic boundary. It's invisible. You cross it in seconds or minutes, depending on the black hole's size. And then you're inside. From there, your fate is sealed. All paths lead to the singularity. It's not a question of steering away or slowing down. Inside the horizon, the singularity is in your future. Not spatially ahead, but temporally ahead. Moving toward it is as inevitable as moving forward through time. For a non-rotating black hole, you'd reach the singularity quickly. For a rotating one, the geometry is more complex. You might orbit inside for a while, spiraling inward. But the end is the same. Infinite density. Infinite curvature. The equations of general relativity break down. Physics as we know it stops making predictions. But from outside, watching you fall, it's different. You slow down as you approach the horizon. Your image reddens as light loses energy climbing out of the gravitational well. Eventually, you appear to freeze at the horizon, your light stretched to infinite wavelengths. To the outside universe, you never cross. You're stuck there forever. Which perspective is correct? Both. Relativity doesn't give a single universal truth. It gives different truths for different observers. And at the event horizon, those truths diverge completely. This duality is part of what makes the event horizon so conceptually challenging. It's not just a place in space. It's a boundary in spacetime where different observers experience fundamentally different realities. And there's one more layer. If black holes evaporate, then eventually, every event horizon disappears. The black hole shrinks. The horizon contracts. Hawking radiation increases as the black hole gets smaller. The temperature rises. For a black hole with the mass of the Sun, the Hawking temperature is about 1/10 millionth of a Kelvin. impossibly cold. But as the black hole loses mass, the temperature increases exponentially. In its final moments, a black hole would radiate at extreme temperatures. The last stages of evaporation might release a burst of gamma rays. We've never observed this. The timescales are too long. But if it happens, it means every event horizon is temporary. The ultimate point of no return eventually vanishes. And when it does, what happens to the information that fell in? Does it escape in the radiation? Is it lost? Is there a remnant left behind, a tiny stable object carrying all the information? We don't know. What we do know is that the event horizon forces us to confront the limits of our understanding. It's a place where gravity is so strong that spacetime itself becomes a trap. Where time and space trade roles. Where quantum mechanics and general relativity clash. And where our ability to observe, to measure, to know reaches an absolute boundary. We can image the shadow. We can measure the mass and spin. We can watch matter spiral into oblivion. But the event horizon itself remains untouchable. It's the edge of the observable. The boundary of the knowable. And standing at that boundary, we realize how much we still don't understand about the universe. But perhaps the most profound consequence of event horizons isn't what they hide from us. It's what they reveal about the nature of reality itself. Event horizons force us to reckon with the fact that the universe isn't fundamentally democratic in how it distributes information. There are places where knowledge simply cannot reach. Not because our instruments are inadequate. Not because we haven't developed the right theories yet. But because the structure of spacetime itself forbids it. This isn't a technological limitation. It's an absolute boundary written into the laws of physics. Consider what this means. In our everyday experience, information flows freely. Light from distant galaxies reaches us after billions of years. Radio waves carry signals across space. We assume that if something exists, if an event occurs, we could in principle learn about it given enough time and the right tools. Event horizons shatter that assumption. They create regions of spacetime that are fundamentally disconnected from the rest of the universe. Not temporarily. Not until we build better telescopes. Permanently. Information that crosses an event horizon is gone from our cosmos. It enters a domain where our physical laws predict their own failure. And yet, we can still interact with these objects. We can measure their mass through gravitational effects. We can track their spin. We can watch as they devour matter and emit radiation. They're not abstract mathematical constructs. They're physical objects with measurable properties. This creates a strange duality. Event horizons are both present and absent. They influence the universe around them while hiding their inner workings completely. They participate in the cosmic dance while remaining forever veiled. The information paradox crystallizes this tension. When matter falls into a black hole, it carries information. The arrangement of atoms. The quantum states. The history encoded in its structure. Where does that information go? If the black hole evaporates completely through Hawking radiation, and the radiation is thermal, random, carrying no information about what fell in, then the information is destroyed. But quantum mechanics says information can't be destroyed. It can be scrambled, transformed, spread across space, but not erased. Something has to give. Either quantum mechanics is wrong, or general relativity is wrong, or we're missing something fundamental about how these theories fit together. For decades, physicists argued about this. Some said information is preserved somehow in the radiation, encoded in subtle correlations we can't yet detect. Others proposed that remnants remain after evaporation, tiny stable objects carrying all the lost information. Still others suggested the paradox reveals a deeper problem with how we think about spacetime at quantum scales. Recent work suggests the information might be preserved through quantum entanglement between the interior and exterior of the black hole. The radiation isn't purely thermal. It's correlated with what fell in through quantum connections that transcend the event horizon. But we don't have the full answer yet. The paradox remains unresolved. And at its heart is the event horizon, the boundary that makes the question possible. What's remarkable is how event horizons connect to other deep questions in physics. They're not isolated puzzles. They thread through nearly every fundamental mystery we're grappling with. Take the holographic principle. This idea suggests that all the information in a volume of space can be encoded on the boundary of that volume. Like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. Where did this principle come from? From studying black holes. From realizing that a black hole's entropy, the measure of its information content, is proportional to the surface area of its event horizon. Not its volume. The area. This was shocking. In normal physics, entropy scales with volume. More space, more ways to arrange things, more entropy. But for black holes, it's the surface that matters. The boundary. The event horizon. This led physicists to suspect that spacetime itself might be holographic. That what we perceive as three-dimensional reality might be a projection from information encoded on a distant boundary. Event horizons became the laboratory where this radical idea was born. They also connect to quantum gravity. Inside an event horizon, you can't avoid the singularity. And at the singularity, general relativity breaks down completely. Densities become infinite. Curvatures diverge. The equations produce nonsense. This tells us that general relativity isn't a final theory. It's an approximation that works brilliantly in most circumstances but fails at extreme scales. We need a quantum theory of gravity to describe what really happens at the singularity. And the event horizon is the gateway to that regime. Every black hole is a laboratory for quantum gravity. A place where the smooth geometry of spacetime collides with the discrete, probabilistic nature of quantum mechanics. We can't peer inside to observe directly. But the event horizon's existence and properties tell us that such a collision must occur. Then there's the connection to thermodynamics. Black holes have temperature. They have entropy. They can exchange energy with their surroundings through Hawking radiation. They obey the laws of thermodynamics. This seems absurd at first. Thermodynamics is about heat, disorder, molecular motion. How can it apply to a purely gravitational object? But it does. And the event horizon is where the thermodynamic properties manifest. Its area is the entropy. Its surface gravity determines the temperature. This suggests a deep relationship between gravity, information, and thermodynamics. That they're not separate subjects but different aspects of something more fundamental. Event horizons are where this unity becomes visible. Looking ahead, our understanding of event horizons will improve. The Event Horizon Telescope continues upgrading its capabilities. Recent observations at 345 GHz, the highest resolution ever achieved from Earth's surface, promise 50% more detail in future images. We're watching the polarization patterns around M87's event horizon change over time. The ring size stays constant, confirming Einstein's predictions. But the polarization flipped direction between 2017 and 2021. Completely unexpected. This tells us the magnetic fields and matter flows near the event horizon are dynamic, turbulent, not static. These observations constrain theoretical models. They test general relativity in the strongest gravitational fields we can access. They reveal how matter behaves in the final moments before crossing the point of no return. And we're finding more black holes. Gravitational wave detectors catch the mergers of black holes we could never see electromagnetically. Each detection gives us another data point. Another measurement of mass, spin, the final state after collision. Each one confirms that event horizons exist. That they behave as general relativity predicts. That the universe really does contain these objects where spacetime closes in on itself. But observations alone won't solve the deep questions. We need new theoretical frameworks. Quantum gravity. A theory that unifies general relativity and quantum mechanics. Until we have that, the event horizon remains a place where our understanding terminates. And maybe that's the most important lesson. The universe contains boundaries we can't cross, not even in principle. Places where causality breaks. Where time and space trade roles. Where information might be destroyed or preserved in ways we don't yet comprehend. Event horizons are cosmic humility. They remind us that despite our progress, despite our equations and observations and theories, we're still grappling with the most basic questions about reality. What is time? What is information? How does gravity work at quantum scales? We've mapped the edge. We've photographed the shadow. We've calculated the radius. But the event horizon itself remains what it's always been. A boundary between what we can know and what we cannot. Between the universe we inhabit and a regime where the rules change completely. And standing at that boundary, we realize something profound. The event horizon isn't just out there in space, surrounding distant black holes. It's a fundamental feature of the cosmos itself. A reminder that reality has edges. That some questions might not have answers. That the universe keeps secrets even from its most curious inhabitants. The point of no return isn't just a place. It's a statement about the limits of knowledge in a universe governed by relativity. So where does that leave us? We've imaged event horizons. Measured their properties. Confirmed Einstein's predictions with extraordinary precision. We've watched matter spiral into darkness and mapped the shadows cast by objects we can never touch. But every answer opens new questions. The information paradox remains unresolved. We don't know if quantum mechanics breaks, if general relativity breaks, or if both theories are approximations to something deeper we haven't discovered yet. We don't know what happens at the singularity. Our equations fail there. Physics stops making predictions. Maybe spacetime itself dissolves into quantum foam. Maybe time loses meaning entirely. Maybe the question itself is malformed, asking about a regime where our concepts don't apply. We don't know if Hawking radiation is exactly right. We've never observed a black hole evaporate. The timescales are too long. Everything rests on theoretical calculations, brilliant but untested. We don't know if event horizons are the final story. Some theories predict modifications to general relativity at extreme scales. Firewalls at the horizon. Fuzzballs instead of singularities. Exotic quantum structures we haven't imagined yet. What we do know is this: event horizons exist. They're real, physical, measurable. They shape the evolution of galaxies. They power the most energetic phenomena in the universe. They set absolute limits on what can be known. And they force us to confront uncomfortable truths about reality. The universe isn't fully transparent to us. There are regions we can never observe, not because we lack the technology, but because the structure of spacetime itself forbids it. Information might be destroyed, or preserved in ways that violate our intuitions about how physics works. Time and space aren't the rigid stage we imagine. They're dynamic, malleable, capable of twisting into configurations where the familiar rules collapse. Causality has limits. There are boundaries beyond which effects can propagate in only one direction, where the future becomes as inevitable as the past, where choice itself becomes meaningless. These aren't philosophical abstractions. They're physical consequences of how gravity works when pushed to its extreme. The event horizon is where our two greatest theories, quantum mechanics and general relativity, collide and produce contradictions we can't yet resolve. It's where the smooth geometry of spacetime meets the discrete, probabilistic quantum realm. Where information meets entropy. Where observation meets fundamental limitation. And that collision tells us we're missing something. Some deeper framework that unifies these pictures. Some theory of quantum gravity that explains what really happens when you compress matter beyond the point where classical descriptions apply. We don't have that theory yet. We have candidates. String theory. Loop quantum gravity. Various approaches to quantizing spacetime itself. But none has produced testable predictions that distinguish it from the others. None has solved the information paradox definitively. So the event horizon remains what it's always been. A boundary between what we know and what we don't. Between the universe we can probe and a realm where our current physics reaches its limit. But boundaries are where the interesting things happen. Where new physics emerges. Where our understanding gets tested and refined. The event horizon isn't the end of inquiry. It's a signpost pointing toward deeper questions. What is spacetime at its most fundamental level? How does quantum mechanics apply in regions of extreme curvature? What happens to information in a universe that allows event horizons to form and evaporate? These questions will drive physics for decades. Maybe centuries. The answers might require technologies we haven't invented, mathematics we haven't developed, concepts we haven't imagined. But the questions themselves are real. Grounded in observations. Encoded in the shadows we've photographed and the gravitational waves we've detected. Event horizons aren't abstract anymore. They're not mathematical curiosities confined to blackboards. They're mapped, measured, studied in detail previously impossible. And every observation confirms the same thing. Reality is stranger than we thought. More subtle. More unforgiving. More beautiful. The event horizon stands as a monument to both human achievement and human limitation. We figured out these objects exist through pure mathematics, decades before observing them. We predicted their properties with precision that would have seemed impossible a century ago. But they also mark the edge of our current understanding. Beyond that edge lies territory we can describe mathematically but not yet comprehend physically, where intuition fails and only equations remain. That's where physics lives. On the boundary between the known and unknown, between what we can measure and what we can only infer, between the questions we've answered and the ones we haven't. The event horizon is that boundary made manifest. A physical edge in spacetime itself. The ultimate point of no return, yes, but also the ultimate challenge to our understanding of how the universe works. And maybe that's exactly what makes it so compelling. It's not just a place where things disappear. It's a place where our theories collide, where our assumptions get tested, where the universe shows us we still have so much to learn. The edge of the observable isn't the end of physics. It's where physics becomes most urgent, most necessary, most alive.